Hello and welcome. In this lesson, we'll explore the chain rule and learn how to use it to differentiate composite functions, which are functions that depend on another. To create a composite function, we'll take a look at this example. Suppose that we are given f of x and g of x, two different functions. To create the composite f of g of x, you see this little circle here stands for of, and it can also be described as f gx, where gx plays the role of the independent variable of function f and is called the inside function because it's the input variable, and f is what we call the outside function, so the bigger function. Then we say that we need to substitute g of x as an independent variable of f of x. So in our case, we're going to say that to build f of gx, we start with function f. So number 2 first. Now we see x, and x becomes g of x, which means that we'll substitute it by negative x squared plus 5. And then we continue writing the rest of the function plus 3. So negative 2x squared plus 10 plus 3 equals 13. To create g of f of x means that we are creating the function g fx. This time f of x is the inside function and g of x is the outside function. So we substitute f of x as the independent variable of g of x. So obviously here we start with the function g of x, so minus first. And now we see the variable x, which in our case has become f of x, which means that it will be replaced by 2x plus 3. So we'll write 2x plus 3 instead of x. X is squared, which means that we have to bring this to the power of 2. And continue writing the rest of the equation of function g plus 5. Expand and simplify, and we get 4x squared plus 12x plus 9 plus 5. Remove the brackets. Negative 4x squared minus 12x minus 9 plus 5 minus 4. So this would be the equation of g f of x. So let's take a look at an example and see how we can use the chain rule to differentiate this composite function. As you can see in here, we have an outside function, x to the power of 2, and for the independent variable x, we have another function inputted, 3x squared minus 5. So we're going to differentiate this in two different ways. This is the way that we already know how to. So we'll expand f of x, which turns into 9x to the power 4 minus 30x power 2 plus 25. If you're wondering how to expand this, remember it's simply a minus b squared equals a squared minus 2ab plus b squared formula, the perfect square trinomial. And now we can start differentiating by simply using the power rule. So we have 36x to the power of 3 minus 60x. We'll try to differentiate this same function, but now we'll use the chain rule. I'm simply writing the equation for one more time here, so we have a nice flow of the solution here. So to differentiate using the chain rule, we say that we first have to apply the power. We have the outside function, independent variable power of 2. So according to the power rule, we have 2. Whatever is inside the brackets, 1 power less, so to the power of 1. Inside the bracket expression won't change, so this will stay the same. But then we now have to multiply by the derivative of the inside function, which in our case is 6x. you can bring the terms together. So we can multiply 2 by 6x. Notice that here we have a multiplication of 3 things. And in multiplication, the order won't matter. So 6x and 2 are monomials. They can easily join each other. And then we have 3x squared minus 5, which in return would equal 36x to the power of 3 minus 60x. Now, one of the things I want to mention is that when I use a chain rule to differentiate, I would leave the answer in this form, which is considered to be the most simplified factored form. With chain rule, we want to write the answers in the most simplified factored form. Okay? So what is the formula for the chain rule? What did we just do here? So we're going to say that if we have a function f of x equals f of gx, then the derivative of the function f of x, the big F of x, would equal the derivative of the outside times the derivative of the inside function. In Leibniz notation, we'll say that d dx of f gx, so the derivative of f gx equals the derivative of the outside. Notice that you don't do anything with the inside function. You leave it as is. That's what we did in our example. So the outside function was x to the power of 2. Okay? And we didn't actually transform or change 3x squared minus 5, which was the inside function. But then we multiplied by the derivative of the inside. So let's take a look at some examples where we can apply the chain rule together. So here we go. We have y equals x squared minus 5 to the power of 7. So we say that dy dx equals, so I will try to identify what the outside function is. So that would be something to the power of 7. So I will start with 7. The power will reduce by 1. The inside won't change. But then I have to multiply by the derivative of the inside, which is derivative of x squared minus 5, or 2x. The next step, I will combine 7 and 2x. That's 14x, x squared minus 5 to the power of 6, and this will be the final answer. In the next example, we have a rational power. So we'll say dy dx. In principle, we do the same thing. Not too different from what we did in the previous example. So we'll apply the power rule to the outside function. So that is 2 over 3. What's inside the brackets won't change. The power is reduced by 1. And inside is still x squared plus x. So then we have to multiply by the derivative of the inside function, x squared plus x. So this would equal 2 over 3 x squared plus x to the power of 2 over 3 minus 1 is 2 over 3 minus 3 over 3. So that's negative 1 over 3. And the derivative of x squared plus x is 2x plus 1. In a better form, now we can write the function as 2. We can bring 2x plus 1 closer here. Down in the denominator, we have 3. X squared plus x to the power of 1 over 3 with positive exponents. Let's do one more. In this example, we have zx equals square root of 2x squared plus 3. Whenever I see square roots, I replace them with powers. It's easier when we write them in power form. So this will be 2x squared plus 3 to the power of 1 over 2. As you can see, power of 1 over 2 will be the outside function. 2x squared plus 3 is the inside function. And I wanted to mention as well that as we go through examples, when you see that something is repetitive enough and you have memorized or understood the process, try the questions on your own. So stop the video and continue working on your own. So applying the power rule, 1 over 2, you don't do anything to the expression inside the bracket or the inside function, but the power is reduced by 1, 2x squared plus 3. And now we have to differentiate the inside, which is d dx of 2x squared plus 3. So the derivative z prime x equals 1 over 2, 2x squared plus 3 to the power of negative half. The derivative of 2x squared plus 3 is 4x. As you can see here, we have some simplifying. So we can simplify 2 and 4. So that will change the derivative to become 2x. And then we can bring this power in the denominator to make the exponent positive. So 2x squared plus 3 to the power of 1 over 2. For more examples, so if you want to actually really grasp a concept and you feel that you need a little bit more practice, chunk the lesson into different pieces. And as soon as we start a new process, you stop there and you start practicing with the one that you have just learned. Now, we're moving on to how to use the chain rule in Leibniz notation. So in Leibniz notation, if we are given a function y that depends on some variable u, where the variable u represents a function, u is gx, if both functions f and g are differentiable, then the function y will be differentiable as well. And the derivative dy dx is given by the formula dy du times du dx. So this is the chain rule in Leibniz notation. So let's practice this together. Now, the first time you see this formula, it may sound very confusing. The way I like to see it is I have dy dx that equals dy du times du dx, and I see that the du's will simplify to leave us with dy dx. Now, technically and mathematically speaking, that's not a straight division because there is a lot more to this definition and this formula than just a multiplication. But that's a way to memorize the formula. So how do we use that formula in order to differentiate a function that is given in this particular form? So as an example here, I brought in the function y equals u to the power 3 minus 2u plus 1, where the variable u, because that's a variable for function y, the variable u in itself is represented by the function 2 root of x. So first, simply write the Leibniz notation. So you write dy dx equals dy du times du dx. So we haven't done anything fancy here, simply wrote down the chain rule in Leibniz notation. So now we start substituting. So the first factor, dy du, is actually the derivative in terms of u of function y, which is u to the power 3 minus 2u plus 1. And this will multiply du dx, or the derivative in terms of x of function u, and function u is 2 root of x. So notice how the variable in the function matches the independent variable in the derivative of that particular function. So here you have u, x, x. When this happens, you do a straight differentiation, and what I mean by that is you simply apply the power rule to differentiate the function. You don't have to worry about the chain or the inside function. Next step, 3u squared minus 2. That's the derivative that we get from the first factor. Now the next one will be the derivative. I usually like to write the powers, the radicals in power form, so it's easier to differentiate it. Now, we have 3u squared, and remember that we are differentiating in terms of x eventually, so we don't want to have u in the answer, so it's time for me to think of substituting u by 2 root of x. So instead of u, we'll write 2 root x squared minus 2, and this will be multiplying the derivative of 2x to the power 1/2. So we have the factor 2, so this 2 in here. And now we are differentiating x to the power 1/2, which is 1 over 2 x power 1 over 2 take away 1. Notice that these two will simplify. And we now have the first factor, 3. Now the power of 2 will apply to both number 2 and the root of x. Number 2 will become a 4, and the root of x will become to the power of 2x. So that equals 3 times 4x minus 2, and multiplied by the 2 simplified, x to the power of negative half. So in return, here we have 12x minus 2 times x to the power negative half. And now we're going to rewrite this in the factored most simplified form, which means we're factoring 2 from 12x minus 2. This is 6x minus 1. And we'll bring x to the power negative 1 over 2 in the denominator to make the exponent positive, and this would be the answer. So let's take another example with Leibnitz notation. So I'm going to add a page in here. So suppose that we have a function y equals 5u to the power of 2 plus 6u plus 3. And function u equals 2x squared minus 1. So if you want to find dy dx, we start off with the Leibniz formula. dy du times du dx. Substitute the function y with 5u squared plus 6u plus 3. So we have d du 5u squared plus 6u plus 3 multiplied by du dx will be d dx of 2x squared minus 1. So we substitute function u by 2x squared minus 1. And now we simply differentiate. This is just the power rule. So that would be 10u plus 6. The derivative of 2x squared minus 1 is 4x. Remember, derivative of minus 1 is 0. And now we bring u in. And that's because we want to differentiate function y in terms of x. So we don't want to see any strange variables there. So we have 10. U equals 2x squared minus 1 plus 6. And multiplied by 4x. So simplify a bit more. So here we have 20x squared minus 10 plus 6 times 4x, or 20x squared minus 4. Obviously, you don't have to write these many steps, but I'm just trying to show all the work and explain everything. And we take out 4. We have 5x squared minus 1 times 4x. So that would be 16x, 5x squared minus 1. So we're moving on now to a new example. And this time, we have a chain and a product rule. So we have the function h of x equals x squared plus 3 to the power 4 times 4x minus 5 power 3. And we want to express the answer in the most simplified and factored form. So let's get started. So we'll say that the derivative h prime x equals, remember that we have the product first, which means that we have to start off with the derivative of x squared plus 3 to the power 4. So x squared plus 3 to the power of 4. So we're taking the derivative of this. And then multiplied by 4x minus 5 to the power of 3. Plus the derivative of the second factor, 4x minus 5 power of 3. Times x squared plus 3 power 4. So start off with differentiating this factor. As you can see here, you have a chain because you have a power 4 and you have an inside function x squared plus 3. So this would equal 4 x squared plus 3 to the power of 1 less than 4, which is 3, times the derivative of the inside function, which is 2x. So what we have done in here is simply differentiate the first factor. And this will multiply 4x minus 5 to the power of 3. Nothing to do there. Plus, now we are differentiating this. So we have a chain again. So the chain is we have a power of 3. And then you have an inside function 4x minus 5. So you start with 3 times 4x minus 5. 1 power less than 3, 2. And then multiply by the derivative of the inside. So derivative of the inside, which is derivative of 4x minus 5, is 4. And then multiply with the other factor. So all we've done in here is differentiate 4x minus 5 power 3. So, and here is an interesting step. If you look at this whole derivative here, expression or a function, you can call it whichever way you want, you see that we have a lot of common factors. So what I do first is I looked at the two groups of factors that I have. Remember, the two groups of factors are separated by a plus here. And then I bring together the monomials, so I write them in a better or cleaner form. So we have 4 and 2x, 8x, x squared plus 3 to the power of 3, 4x minus 5 power of 3, plus 3 times 4 is 12, 4x minus 5 power of 2, x squared plus 3 power 4. And then I search for common factors. I start off with the monomials. I have 8x and 12, that means 4 is common. And then I continue with the binomials. We have x squared plus 3 repeating in both of them. And here we have a power 3 and here we have a power 4, which means that x squared plus 3 is a common factor. And the power we take out is the smallest one because that's a common power for both. And last but not least, we look at the last factor here, 4x minus 5. It's a common factor. Then we have powers of 3 and power 2. So 4x minus 5 is a common factor. And the smallest power, between 3 and 2, we have 2, is the common power. And now we try to figure out what we have left from each group of terms. So 8x, 4 is out, that means 2x is in. The next term is x squared plus 3 to the power of 3. The whole thing is out, nothing left from x squared plus 3 here. The last factor in the first group is 4x minus 5, power 3. 4x minus 5, 2 powers are out, 1 power still in. So multiplied by 4x minus 5. Plus number 12. Number 4 is out, so factor 4 is out. That means 3 is in. 4x minus 5 to the power of 2. That's all out, nothing left here. X squared plus 3 to the power of 4. We have x squared plus 3. 3 powers are out. That means 1 power must be in. So x squared plus 3. All we have to do now is simplify. And we have 8x squared, simply expand, minus 10x plus 3x squared plus 9, which is 4. X squared plus 3 to the power of 3. 4x minus 5 power of 2. 8x squared plus 3x squared is 11x squared minus 10x plus 9. So this is how we use a chain rule to differentiate the product of two factors. So the next example is the example of a quotient rule and a chain. So we have a power of 10 and inside function is a rational function. So we start off with the power. So g prime x equals 10. The power now will reduce to 9. Inside doesn't change. And then we multiply by the derivative of the inside. So I'll write here d dx of 1 plus x squared over 1 minus x squared. This is not a step that you must show normally, but we're just explaining things again. So we have 10. Nothing changes to this term. 1 plus x squared, 1 minus x squared, inside function, right? And now we start differentiating by using the quotient rule. Remember, the quotient rule is f over g prime is f prime g minus g prime f over g squared, right? So the derivative of numerator 2x multiplied by the denominator 1 minus x squared. Take away. Derivative of the denominator is negative 2x multiplied by the numerator 1 plus x squared. All of this will be to the power of 1 minus x squared to the power of 2. So next step, 10. And I'll do something fancy to this power in here. So I will assign the power of 9 to each numerator and denominator. You will see why. Or you've probably already seen why. So 1 plus x squared to the power of 9. 1 minus x squared to the power of 9. Now, inside brackets, I will have to simplify the numerator. So we have 2x minus 2x power 3. Now, these two minuses will make a plus. So 2x times 1 plus 2x plus 2x to the power of 3 over 1 minus x squared to the power of 2. So we have a fraction. So this is 10. 1 plus x squared to the power of 9. 1 minus x squared to the power of 9. Multiplying 1 minus x squared to the power of 2. And numerator will be 4x. As you can see here, we have 1 minus x squared, power 2 and power 9 together will combine to make a power of 11. So 1 minus x squared, power 11. And here we have 10 and 4x, 40x, 1 plus x squared to the power of 9. And this is the answer. So I hope you enjoyed the lesson, and I hope everything made sense. And thank you very much for listening. Bye for now.